All right. So let's start this right off the bat. File, new. I'll go ahead and turn my surface back on. Right? This is the surface I originally built out of Grasshopper. This is the surface that determines every single step of the way from here on out, right? This is the master of the geometry, right? Yeah. All right. So I have these ribs, and I remember that I divided it 10 by 10 times. So I'm just going to simply bring this into Grasshopper and do the same thing, right? I have something modeled in Rhino. I need to bring it into Grasshopper. I can use one of these params placeholders like surface, right-click, say set one surface. Now I can select a Rhino piece of Rhino geometry, bring it into Grasshopper, start to build inside its parametric space. All right. I'm going to go ahead and turn that layer off just so I can sort of see as I go without that gray grass or Rhino preview in the way. All right. This is a little bit of review from all the stuff you watched last couple of weeks. But what I'm going to do first and foremost is simply divide the surface up into those checkers, into columns and rows. And then make sure that each quad in those columns and rows, and that sort of spreadsheet, if you will, the sort of warped spreadsheet, becomes their own little quad surface, right? So we can consider a surface a two-dimensional domain, and that it has latitude and longitude, u and a v. So now it asks us how many times we want to divide the surface in the u direction and in the v direction. I would assume that that's a variable. Of course, most of you have already locked that in when you ran your Rhino script, but let's say the minimum is 8 by 8 and the maximum is 10 by 10. So I'll go ahead and set these up like so before I put them in. Make a copy. There we go. Okay. Now, what that does is that just looks at that latitude and longitude values and divide them up 10 by 10 each, right? But now we actually need a way to sample those sort of patches from the surface itself, right? So if we go to surface, fortunately there's an isotrim command, which basically wants a minimum latitude, minimum longitude, maximum longitude. You feed that in, suddenly it gives you a quad, right? And so we can give it this surface, we can give it a list of all of these, and we get a list of quads out, right? In fact, 100 of them. Not a huge surprise, because we're dividing it 10 in the U and 10 in the V. 10 times 10, 100, right? Okay, so moving along, I think we all sort of understand that intuitively, right? It's intuitively obvious to even the most casual observer at this point. Sorry, I used to know someone who talked that way. I'm just going to start to build something here. First of all, maybe I'll just go ahead and explode each of these so I can find their faces, their edges, and their vertices, right? So 100 quads, now I have 100 faces. Each one of those 100 quads has also 4 edges each, and each of those 100 quads have also 4 vertices each, right? Since they're quads, we know, pretty stable, it's going to have 4 edges, 4 vertices. That's the definition of a quad. Right, so let's see here. There's vertices, and what I'm going to do is I'm going to take out each of these vertices. You remember, I can take this list of 4 vertices from each one. I can sort of say, let's take the first set, and the second set, the third set, the fourth set, with a simple nth item list widget. I'll just copy it. Damn, 4 times. There we go. And each time I'm just going to say I want the first value from each of these, and the second. So I'll go ahead and change this index to 1, since we start counting at 0. The first is 0, the second is 1, the third is 2, and the fourth is an index of 3. Because computers aren't quite like us, are they? As we're learning with artificial intelligence as well. All right, so there's vertices. What else? I can take each of these faces, and let's go ahead and find a center point. Let's see here. Let's evaluate the surface, each of these surfaces, each of these faces, at a UV parameter, right? So this is giving it a very specific latitude and longitude coordinate in order to place a point on each of these checkers, right? Each of these quads. I can do that quite easily, actually, with the multidimensional slider, right? Which moves around much like if you were looking at a spreadsheet And I'll just go ahead and reparameterize these. Now you can see I can move these along the surface, or I can say 0.5, 0.5. But anyway, I digress. So let's see. I have these edges. Let's go ahead and do these with the edges too, and just start to get edges. Second, third, fourth, first, second, third, fourth edges. Yeah, let's move those around just a little bit more so that they're separate from the vertices. I don't get confused. All right, so I have faces, and I have vertices, and I have edges. What's that?
I'm sorry, I missed the step where when you put evaluate the surface, what is the box next to it?
A multidimensional slider. So I give it a coordinate
Where is that found here?
in the parameters tab by the regular number slider. All right. Now, let's see. We have a point, we have a point, we have a point, a normal, and a frame. Right. So what I want to do, let's say I want to project up from that evaluate point, right? I have a normal direction. I can do that. Let's say curve, start point, direction. Start point, direction is the normal. Length would be something that I actually make as a variable. Let's say I want to go somewhere between -2 and 2 inches, right? Because we're dealing in inches here as units. So just keep this in mind. I don't want to go too much deeper or better than that. Go ahead and turn this preview off just so we can see what we're actually dealing with here. Yeah. Okay. So now I have a sort of apex of a pyramid, right? In this case, that's what I was basically doing before. What I did, instead of just making 2 edges, though, I started to actually create another set of points I could move and slide in, make this thing sort of fold in and out, right? So let me try that. First of all, as you go, you might notice that some of these things start to get in the way. I'm going to turn the preview off on some of these things. They're still there. They're still being computed. I'm just asking it not to show them so I can sort of unclutter my screen a bit, right? Oh, yeah. And let's see here. You can still see I have those edges and those vertices. Yep, there they are. You know, those edges, look at the edges, right? These things were actually, the surface was actually curved, so the edges are actually curved. But we're actually made up with basically the polyline equivalent of that based off the Rhino script that we did, right? So one of the first things I might do is simply throw out these edges, and I'll make my own linear edges by simply connecting the right vertices where I need them. So this kind of gets a little hairy here, but you can see there's the first set. It starts there, right? So sort of, we can follow this around a bit and sort of see what's highlighted and what's unhighlighted in order to understand the sequencing here. I'm going to go ahead and move these back up, though, where we can sort of see everything all at once. And what I'm going to do is I'm just going to maybe draw a set of straight lines between each of these vertices. So I'll go ahead and do that one. I'll make a copy. I'll go ahead and do this to that. And then this one to that one. And then this one all the way back to my first one. Yes. All right, now I have a set of straight lines that actually correspond to the edges of my ribs. That's helpful. And now I can actually see what I'm dealing with here. Yeah, look at that. All right. In this case, the shading component that I did, and I'll just go ahead and do this since it demonstrates what you have to sort of think about, right? How to make points in space, and how to then start to connect them up by connecting the dots, is to simply look at these curves, and first let's go ahead and evaluate them at a t parameter. I'm going to go ahead and just find one point along them, right? Just like we did before. I have 4 lines, so I'm going to have to make 4 of these and plug each one in at a time. Now I can actually connect alternating points. So I can connect that one and that one. And I can connect this one to this one. That one to that one, and this one to this one, right? Yeah, not too shabby. Yeah. All right, so from there, I need some points, right? So let's go ahead and make some points. Now, it's not lost to me that maybe you're trying to figure out what I'm doing. So it's basically this, right? Again, when in doubt, sketch. Our superpowers, architects, right? Draw, draw, draw. Get this active out, start building and cutting, right? So, what I want to do is I want to find a point up here, and I want to connect these things, right? Except, I want to actually do something just a little more complex. I'm going to actually create a crease here, and a crease back here, right? So that's why I'm trying to locate a point along this line, and a point along this line, so I can connect triangle, 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 triangle. Right, so now with these lines, I just need to, again, place a point. So it's a lot of construction geometry. It's almost as if you were constructing this back at home on your desk with a T-square. You have to like sort of make all of this construction geometry just to find certain points, connect things up. Have any of you ever done that when you're like, actually have to construct an axonometric or construct a two-point perspective? Yeah, it's a pain in the ass, but it works, right? In fact, it's how we did it pre-computers, right? Pre-digital computation. So, let's see here. Let me go ahead and see what happens when I plug this same number slider in for each. Not too bad there. Yeah, I like that. Okay, so now I have a set of points I can start connecting the dots with, right? Now it looks pretty complicated because I'm seeing 100 of them all at the same time. So let me just sort of see if I can zoom in on one cell and we can sort of keep this problem in front of us, so to say, right? Let's just look at this cell right here, okay? One last thing, right? That line that I projected up, I need its endpoint. So I need to go ahead and find the start and end point of that bad boy. There it is, right there. Okay, and so what I want to do is I want to start drawing triangles between this edge, and that point, and then this point, and that point, right? So I'm just going to follow along here really carefully and make sure that I'm connecting up the right things. But first, I'm just going to make a surface from vertices, right? I can do that with 3 or 4 vertices. If I do it with 3, I get a triangular surface. What's important about a triangle? Anybody remember this? They can be strong, but what's really important when it comes to planar fabrication of triangles? Triangles are always planar, right? Quads aren't necessarily planar at all. In fact, it'd be real fluke if they were, right? All 4 points have to coincide in the same plane. Triangles, that's the minimum you need to define a plane in space. It's always going to be planar, right? So we know if we start with triangles and we have triangles and we're unrolling triangles, that they'll flatten back out planar because they already were planar. All right, so we can do it without bending, stretching, tearing. Okay, let's see here. First of all, I know all of these are going to connect up top. So I'm going to go ahead and plug in that end. And let's just try to find the right points here. So I have this point, and I want to just basically make a triangle from here to here to here, right? Okay, so I'm going to go ahead and plug in that point. Sound effects, of course, are always optional. Now I want to try to find the right vertex, the right vertex here. Is that it? Oh, no, I don't think it is. It must be this one. Nope, let's see, which is it? It's this one, okay. Let's try this out. Aha, there we go. All right, not too shabby. Now, I know that the next one's going to have this same point and this same point. I just need to switch the vertex down here to this vertex. So let's see. Is that the correct one? No, it sure isn't, because it starts there. That's not it. Ooh, that's not it. Must be that one by process of elimination. Oh yeah, look at that. Right. So now I can open this up further or less, right? I can sort of change this. I could also change where that apex is. Right? All right. So I'm starting to build a fairly robust chain component just from a few simple pieces here. I just need to do this twice more, right? So let's try this. Now in this case, I just need to go from here to this point. So that middle point I'm going to change to this one. Yeah, there we go. Ta-da! Always good when some plan comes together. And last but not least, I need to switch this last one out with the right vertex. That's not it. I need this one. That's not it. That's definitely not it. That's not it, so it must be this one. All right. Ha, yes. Now, if I unroll these, I have to unroll 4 different surfaces out, and they're all going to be scattered all over the place. What I've noticed is that I smartly, and this is something that you need to think about, steps ahead, right? How these things actually have edges that meet, so that you can join these things together. The more joints you have, the more gluing and holding the time it takes to assemble exponentially grows. Right? Now, you might have a lot of time in your hands at home, but when time is money and you're in, like, say, a dense urban core, imagine doing this in the middle of Manhattan, Hong Kong, or Istanbul, right? It gets really expensive. The more you can sort of, the more on-site labor that you can minimize, right, the less expensive construction is. So, in this case, and the less room for errors, right? You know, the more joints you have, the more errors you build into the system. So we can think about these again as just sort of folds, right? One piece that can be laid out, and then you score it in a couple places so you can fold it, right? And you don't have to worry about gluing 4 triangles together and gluing it to the frame at the same time. That'd be terrible, right? I wouldn't wish that on my worst enemy, to be honest. So what we're going to do is we're going to take each of these, we're going to go to the Surface tab, and let's say join, right? So we're going to join this into a BREP, or basically the fancy word for polysurface. Now, instead of having 100 triangles and another set of 100 triangles and another set of 100 triangles, and yet a 4th set of 100 triangles, we have 100 polysurfaces, right? Okay, so each component is its own polysurface. All right. So up until now, this is kind of what you're supposed to be doing anyway, right? Yeah. All right. So let's see here. Let's unfold these bad boys, shall we? All right. So, yeah, hot damn. Let's unfold these. So if I go to my Lunchbox tools, you can see I have a bunch of plugins installed. But if I go to Lunchbox tools and I go to utilities, there's something called Unroll BREP. Surprise! We have a BREP, a polysurface. We want to unroll it flat onto the XY plane. This is the tool to do it. So I'm going to pull this out. I'm going to look at the inputs. The first one is the, I don't know what it's doing here, is the BREP, or list of BREPs to unfold. And then there's a second input. Do you want to keep all these things joined together? If they're a BREP, do you want to explode it, or do you want to keep it joined, right? So join, it's kind of a join question mark. It's automatically set to false. I'm just going to go and set that to true. I'm going to keep them all joined together. I'll just plug these in. And here's where it unrolls them all out on the 0, 0 plane, or on the 0, 0 points on the XY plane. All right. So now what we have to do is we have to spread all these bad boys out. I don't like to do that manually, especially when I have Grasshopper. So what if I said we could actually build a grid quickly, point grid, and then move each of these to its constituent points, right? Then we could sort of make that grid bigger, smaller, to sort of get these things as tight as we can on the 8.5 by, or 18 by 32 sheets, right, for laser cutting. But at the same time, make sure that we don't have any overlaps, right? Because that can't have overlaps. Right. So anyway, let's do that. I go back to day 1, week 1, where we simply made a list of numbers, an ordered list of numbers. We did that for x and y. We cross-referenced them, plugged them in for x, y coordinates to make a set of points, right? Old news, right? That was like 101. So if I want to make a list of numbers, let's go to sets, sequence. Let's make a sequence. Let's use series, right? Anybody remember series? It's a real quick common recipe for making an ordered list of numbers. The first number, the step size for each successive number, and the number of successive numbers, right? Okay, so how many do we need? Well, we said over here that we need 10. So let's go ahead and just plug that in for the number that we need. And the first number will start at 0. Sure, why not? Let's try it. And the step size, or the spacing between our sort of x and y coordinates, right? Maybe we'll make that a variable. Right, we'll make a number slider. We'll give ourselves some breathing room here. Okay, and so I'm going to go ahead and do that twice. I'll go ahead and plug in this. Now I need to go to the sets. I need to cross-reference these together. Right? Old news. Quite old, actually. And then what we can do is we can find that, let's generate points from x, y, and z coordinates. So plug these in for the x's, plug these in for the y's, and we have a grid. Ta-da! All right. Now let's move this over. How many of you have noticed, by the way, that if you select all of these things and you say, this is my grid making set, I can select them all, and I can hit Control-G, and I can group them together. And then I can move the group around, right? And I can begin to actually think modularly about my tools, right? I can have this one over here that divides the surface, and have this one over here that starts to connect a bunch of things up, and have this one over here that unrolls, and have this one over here that creates labels, and have this one over here that makes a grid, or whatever it is, right? Okay, so, and then the other thing I'm sure maybe some of you have noticed, let me just go ahead and get rid of that, is you can always use this notepad widget and start to enter in comments or labels, right? So a month from now when you open this thing back up and you go, man, I'm really tired and I hardly remember any of this stuff, what the hell is this, right? You can actually go through it step by step if you actually make your own comments and labels and things like that. So anyway, I'll go ahead and group these together and move them on over, right? What I want to do is I'm going to take each of these. You can see that there's basically 0 to 99, 100 tree branches. Inside of each of those is a list of one item each, one of those unrolled VREPs. And I want to move them. So I'm going to go to transform. That's how I move things, rotate things, scale things. Just like in Rhino, here in Grasshopper, we have the same stuff. There's move. And what we can do is we can say, let's move this stuff, and let's move it using these translation vectors. So let's look at this really quickly, right? This is a data tree, and this is just a list. So if I'm going to hook this up to here, I want to make this a data tree also, right? So I'm going to right-click on the output. I can say graft it into a data tree. Okay. If I don't do that, look what happens. It starts to take each item from here and start to put it through every single point, and I have like 100 things unrolled on each surface, right? So what we want to do is we want to make sure the data matches. So I'm going to go ahead and just graph this. There we go. All right. Now, you can see that the original unrolls are still there. I'm going to turn off those previews. You can see that our grid needs to be spaced out better so that we don't have the overlaps. There we go. Now we're cooking, right? Okay. Now, these are surfaces. You can tell because all I see are red fills. I can see the edges. Laser Cutter just wants lines and curves, right? It doesn't want surfaces. So what I'd like to do is now take each of these and find all of their edges. And not only that, I want to know which edges are around the outside and which are on the inside, the interior versus the naked edges, right? That's how geometrically we usually refer to these things. So let's take each of these now. There they are. And I'm going to go ahead and go to surface. I'm going to find all of its edges. Yeah, there's one called BREP edges, right? Polysurface edges. I can plug these in, And look at that. It gives me the naked edge curves, the interior edge curves. If I select this, it gives me all the outputs highlighted in green all at the same time. I'm just going to go ahead and turn the preview off, turn this preview off, and let's just pull each of these out on their own. I'll just make a little curve widget, and let's just look at the outside ones, right? And then we can always look at just the inside ones, right? So I could then bake these out onto the red layer and bake these out onto the blue layer, right? Keep everything nice and straight. Again, it's all about managing data at this point, right? Like, you know what you want to do. I've scaffolded for you, right? It's a matter of, can you go through the motions and make the software work for you instead of the other way around, right? Okay. Make the machines working for us. That's always half the battle, at least, isn't it? All right, so there, right? Those are ready to laser cut. Now, I don't know about you, but when it comes to building, like, I like jigsaw puzzles. I don't like puzzles when it comes to, like, I'm really tired, it's at the end, and I'm trying to put together my architecture model, right? Yeah, right? So we need to label these, because each one's slightly different, and each one has its own place. Just like Radiohead said, everything in its right place. So, let's do that. I need to make labels. Guess what labels are? Text, or numbers, right? In fact, I can just number these. 0, 1, 2, 3, 4. Except the bottom's gonna be 0, 0, the very far end's gonna be 9, 9, then, one other corner's gonna be 0, 9, and the other corner's gonna be 9, 0, right? And that way we can keep track of things. It's just like if you look at a spreadsheet and you have the alphabet on one end and the numbers on the other end, A1, right? It's like playing Battleship. Except, let's do it really simply. Let's just think number, all right? So first and foremost, we have our grid builder here. Let's build a list of numbers for our labels. Let's make a label maker. Let's see, let's build this bad boy. Again, let's go to sequence, let's go to series. Let's make some numbers. All right, so again, I need 10 numbers, starting at 0. So since I've linked this to the U count and the V count, I'll go ahead and just link them up again here. So that way, if I decide to go 8 by 8 instead, it won't break when I change the sliders at the very beginning. Everything will update with them, right? Just smart thing to do. Use the same variables throughout. All right, so let's see. We have 0 to 9, 0 to 9. Let's cross-reference these, right? We want to sort of think of them in a sort of grid configuration. All right, and now we have a list of 0, 1, 2, 3, 4, 5, all the way to 9. We have that 10 times. And then the other list here that we're giving is probably 10 zeros and 10 ones, 10 twos, 10 threes. What we can do is we can combine these. Let's just go ahead and do that with a string. Let's pull these together. I'm going to go ahead and graph these as a tree so that it doesn't just graph the whole list together, but it takes the first limb with the first limb. Right, okay. So let's test this out. Let's see what we have here. What I'm going to do next is I'm going to make a tag, a text tag. You guys ready to make some more text? Oh yeah. So if I go to display, you can see that there's several different text tags here. One's a 3D text tag, and I'm going to go ahead and use that. And it's going to ask us for the location orientation for each piece of text that we want, the label, right? And then what's the actual content of each label down below that, the T, the text. So I'm going to go ahead and plug these in for text. Okay. And now I want to go ahead and put these at each grid point. So I'm going to go ahead and bring this all the way over here. And here's my grid. It's over here, right? Someone agrees with me. Nice sound effect. Well done, whoever that was. A+ for you. All right, and I'll go ahead and give it something for size here. And let's check this out. Right, so one other thing you might notice here, right? We're generating text tags. We're generating a bunch of unnecessary ones. And that's because, again, I have a data tree plugged in for one and a list for other. So I'm going to go ahead and just graph this into a data tree so that they match up. Now you can see that each one's labeled. I can shrink this down, right? At this point, you can try to fiddle around. Use whatever effort you want there. You can fiddle around trying to get this thing in position just right grasshopper. Or you can just make them out in their own layer, select them all as text, change their font one time in the style, right? I'll go through that in just a minute. But again, it's not lost on me that it's not maybe clear where 0, 9, which corner over here is 0, 9, right? So I want to actually apply the same labels to the corresponding quad back in the surface. So I'm going to go ahead and do that as well. So, well, I know I need a text tag. I'll go ahead and copy that bad boy. I just want to change its location. So instead of at each grid point, I'm going to go with, remember, each face in the cell has a frame, a tangent frame. Let's do that. Beautiful. Now each cell has a number as well, corresponding number. Right? So now we can tell which corner is 0, 0, which corner is 9, 9, 0, 9, 9, 0, right? We can refer back to this. We can look at it relative to our assembled grid shell. Now we know exactly where 0, 0 goes. I fold it up, I start to glue it on the right cell. Okay, we're just one quick step away from laser cutting this bad boy, aren't we? All right, so let's take a look at this really quickly. That label looks way too large for me, my taste. What are they like bowling up there? Like, what the hell? Is it a bowling alley? All right, anyway. I'm just going to shrink this down. But one of the things I might do is simply make a set of layers very precisely here, right? I have cut and score. So maybe I put the active layer to cut. And I'm going to go ahead and select these and bake them on the cut layer. The interior curves that I just want to score, I'll bake those into the score layer. These text tags eventually are going to go in the score layer, but I might just make their own layer for a moment here. Sorry if you guys can hear me over this. And I'll just say text labels. And I can always I can turn the color and I can change it. And let's make it 255 blue and then 0 for each of the others, so it'll score as well. What I'm going to do is I'm going to take the tag. I'm going to go ahead and bake these into that text labels folder or a layer. Okay. Now you can see that all that formatting is all lost, right? What I'm going to do, that's text. I'm going to say cell last, if it was the last thing I created. There we go, all that text, right? Or I could say cell text, right? Select text as a command, just select it all at once. I can go to again, the color wheel, the properties. I can look at the text properties, and I could just, again, change all of the properties here all at one time. So here's where I would say, I really don't know what Segoa UI font is, but what I really want is single line font Rhino Architect, and that way I minimize the amount of cutting time and scoring time I need. And then the height, that still looks way too small to me, or way too large. So I'm gonna go ahead and shrink this bad boy down. And let's just go with 0.05, right? And now I can say move, and I can just move them all into the right place that I want them, right? All at the same time, hopefully. Okay. Now I need to start distributing these around in that 18 by 32. I probably could have tightened these up a little more. There's nothing saying I need a quarter of an inch or half an inch between these things. As long as they're not overlapping, they can even touch, right? As long as they're not overlapping, you're all good. So I'm going to minimize waste, maximize yield. I didn't do that in this case, but I just wanted to go through the steps with you, right? Again, if you know what's going on, don't worry, I got you. And you can think a few steps ahead. You got this, right? Now, there's a couple of things before we get to questions. But raise your hand again here in a minute. Before we get to questions, there's a couple of things here, right? You don't have to make something super complicated and then repeat it 10 by 10 times to make something look really cool. You can start with something relatively simple, right? Simple set of parts, simple set of rules, repeat. The repeat is what makes it really interesting, really lovely, right? Both in terms of the texture that it creates and then also the shadow patterns that it casts on the ground, right? So something to think about. If you're having a hard time and you have, well, I have like 30 pieces, it's like, stop it. Boil it down to 3 pieces, right? Like, I mean, you kidding me? Like you're working with chipboard at this little itty bitty scale, right? It can't be overly complicated, right? There's a certain scale, and a certain amount of complexity you can sort of take care of at that scale with a certain material, right? So be smart, right? And just be clear about it. Like, hey, look, I started with this, but you know, I had to sort of scale things back, and I'm getting a similar effect anyway, right? I decided I didn't need like 13 different edges to glue. I only have 2 now, and that's going to save me probably a good 40 hours of work, right? Okay, so does that make sense? So I don't want you to do a simple, you know, half pyramid or anything like I was doing, right? That's just too easy. But, you know, try to find something that you actually enjoy and like, and that you want to have repeated 10 by 10 times, that you do want to actually sort of laser cut and put back together, and, right? You know, I've seen all kinds of interesting examples, right? We've had them. I don't keep all of them. I let them have them back if they want them. But I've had folks that do things that go in this direction and in this direction, right? If you think about the section of this thing, I've had people that sort of subvert my understanding instead of setting them on top. They go down into the cell itself. I've had folks that try to shingle things. It's hard to do. You have to be careful doing it, but it is possible if you'd like, right? But again, don't overdo it, right? You can't. There's only so much one person can do in a short amount of time, even with the laser cutter. Right? So again, scale your complexity to the problem at hand, right? Don't go overboard. You can't go super simple like just a 2-sided pyramid like that. But don't go overboard. Okay? You can always scale back. At the end of the day, what I'm looking for is, were you able to go through this? Were you able to sort of have command over Grasshopper? Were you able to get things out and produced to a certain level of craft and care and attention, going back and forth between the digital information, a laser cutter, and everything else, and glue, and chipboard, right? Chipboard isn't perfect, is it? How many of you bought chipboard and you're like, oh shit, I didn't realize it, but this corner is all gummed up. Like, what the hell do I do now, right? Or you know, maybe it's apparent that it's been there for a while, and so some of them are a little thicker than some of the others, right? Because of expansion, absorption of moisture, etc. Right? Even plastic absorbs water and can shrink or expand out of tolerance. Right? Trust me, I used to. Back in my old institution, we bought some machinery. The school didn't know what to do with it, so we found a plastic vacuum former company outside of town that would house it for us, paid for electrician to come in and wire it all up. But it was really interesting. They had it down to a science of how many doors they could open to change the temperature or humidity before things started really screwing up. And that was vacuum forming plastic. So keep that in mind, right? Like tolerances are tolerances are tolerances. And I understand chipboard has a sort of tolerance, not quite like aluminum or plastic, but better than you would think, right? Better than, let's say, 2x4s in wood that are all twisty. None of those are straight. You guys notice that? Anybody ever try to beat 2x4s together into a frame a wall? You guys worked with that? Who here has worked for a framing crew? Yeah, it's tough work, right? You learn quickly how to sort of do that, how to be quick and efficient with it. But one of the things you also understand is that nothing's really straight, right? So you're trying to, it's about how you distribute error across the system. So anyway, here we go, right? Like now I'm ready just to sort of make sure that these things fit in 18 by 32, rearrange them if I need to in order to make that happen. And that's how it's done, right? Now, this example, I've already built for you guys. That's what I opened up at the beginning. It's already linked up in Canvas. So you can go ahead and use it, look at it. the first part, right? That you were already sort of working on that, but then how to sort of join everything together, unroll it, start to make labels, all of that sort of done for you, and we did it today in class together as well. Conceptually, what sort of went way over your head, or is it, or when we break it down and we're reductive and we break it down into chunks, does it make relative sense? Right? It's about managing a lot of complexity. It's about making sure that you're connecting the right points. It's about making sure that you're plugging in the right number of divisions from the very beginning. And you realize that if you change them there, then you also have to change them here and here and here, right? You know, it's not enough just to say this is how many times I divide the surface, but it's also the number of points I need in my grid, right? It's also the number of parts I'm going to unroll. It's also the number of, the number of labels I'll need, right? So thinking about these things step by step, I think, is hopefully helpful for you. All right, how are we doing on time? It's 11 o'clock. So what questions do you guys have? Yeah. When you what? Like overlap dramatically? Right, so you could be looking at these, where you first initially unroll them and they're all going to overlap. I just turned that off. Or it could be the spacing of your grid. They're just not spaced out enough, and so they're overlapping, in which case you just need to space out your grid better. Okay? Does that make sense? Okay. Yeah, you had it up much earlier.
Are you putting in these scripts in the,
Yeah, they're on Canvas.
these scripts for Grasshopper?
Yes, so for today's, for instance, right, it's already here. And there's already a placeholder for the recording I'm making right now. As soon as class ends, I stop the recording, I start getting uploaded to YouTube. It takes a while for it to process in YouTube, but I faithfully embed it into Canvas so you don't have to go to YouTube.
And just a quick question, you were mentioning about like having like these lists with like pre-made scripts. Where do you keep those? Do you just like save Grasshopper files and keep a list of, or do you say just keep them in the original file?
Oh, like when I make like it depends, but oftentimes I just keep them in, I don't necessarily break them out as their own file.
That's what I mean, you don't break them out.
Not usually.
Refer, like,
Or I can always open them back up later and copy and paste part into another. Yeah. So I'm thinking sort of modularly about, yeah. Okay, I got what you mean. Yeah, I don't necessarily think of that far ahead. But if I'm encountering a problem, I go, I've done this before.
you find that project.
I can go back, and if I need to, if I kind of want to try to remember what I did, I can always go back and copy and paste from one to the next. Okay, what was your question? Thanks for your patience. Regarding what?
Regarding the letters,
Yeah.
there's some minimum size for the laser in Explorer, or like we can go over the data.
Oh, like for the labels? Make them as small as you can. They can still read, right? You don't necessarily want to have to like look at each one with you have to wear the mad scientist goggles with the magnifying glasses. I used to have a pair of those when I built robots. We would unpack and then repack. We would unpack little servo motors, and then change the gearing and then repack them. That was precision work. We would have. Actually, can't even imagine doing that now with glasses. So yeah, I mean, I'd say it's here's what I'm hearing, right? Like how small can you make them? Is there a minimum size? They're going to be on there. Trying to figure out where there's a place you can put them so that there aren't. Here's an interesting thing. Look at it and see if you can figure out which way it folds. And if you can flip your like mirror all your line work and put them on the back of like the underside, right? Or again, like what I did is I moved them all at once, so they were at least at a set position from one to one, so they weren't like accidentally all rotated around against each other or anything, right? So use it as like maybe you leave them in there as sort of evidence of how this thing was made. They're going to be in there in one way, shape, or form. The question is, how obvious are they going to be, or how hidden are they going to be? but you can go pretty small with them. Again, it's more of how well you can read them than how small you can read them. These are all excellent questions. More will pop up. What I propose is instead of Wednesday moving ahead and talking about performance, we can cut that part out. I can maybe do some demonstrations for you guys at a later time, just sort of showing you what that looks like. But what we can do is Wednesday will be a work in class day. And I'll float around, and if some folks are really stuck and nothing done stuff. And if you have just a little thing in your way, I can help you with that little thing in your way. We still have about 10 minutes left, but if there aren't any like larger questions, we can end class early. If anybody brought in some laser cut prototypes, you can take a quick look at them. Just carefully, don't bump into people as you're moving out. They might have laser cut prototypes. You know, they don't want you crunching up. You guys feel good about this? I mean, at the end of the day, like, these things always look immaculate. Like, I'm surprised, actually, like, between the first try and the second try, a lot of improvements happen. Right? Like, you guys are really bright, really smart. You do it once and you just adjust, right? And that's the sort of convenience and luxury you have here in school is, think of these as prototypes. You can sort of afford to build it at this scale anyway, before you would build it, you know, a couple times before you would build it at full scale, right? To sort of work out some of those kinks, those tolerances. You can understand the constraints of materials. You can understand the constraints of scale, to try to figure out if the labels make sense and how you sequence the assembly. If there are ways you can begin to think about choreographing the steps in the assembly even, right? It's not lost to me that for some of you, you might actually have components that from cell to cell share a common edge. You could actually try to make strips and join them together, and then suddenly instead of having 100 pieces, you only have 10. But they're a set of strips and poles, and you're sort of placing them along a row, right? That happens occasionally, right? Depending on how you're thinking about the geometry, how they relate to each other cell by cell, right? Quad by quad. Right? So on Wednesday, we can take a more granular look over everybody's shoulders, so to say, while you're working. I can help troubleshoot as much as I can. At that point, I could say if you're still having issues, then you can just email me and set up a time via office hours to sort of come in, or we can, you know, outside of office hours, really, to come in, and I can help you out individually beyond class, just to get you really on your way. Again, remember, we have this week, and then a week from today we don't meet, but then on that following Wednesday, I want to see the next iteration, the next prototype. So if you haven't, sign up for laser cutting time now, so that you know exactly when that next deadline is set. And I can prioritize who I help when, based off of that order, right? Based off of that schedule. Otherwise, you know, I get the same 3 people, and I love these 3 people because they always ask me questions, and they always ask for help, and it's perfect, right? But you know, if a lot more people than 3 people need my help, then sort of understanding when the deadlines are can help sort of prioritize getting that help. I mean, let's just be smart about it. But again, we're always looking at in advance. Look, I understand now that I say this, right? And some of you are like, oh shit, God, yeah, I do need some information. Everybody's in a rush and sign up for laser meeting time. And there'll be some folks who don't get laser meeting time until the day of. The day after, right? Again, you guys have been fairly careful and good about just letting me know that, right? And if it feels right, then I would say, okay, well, just come in the day after, right? You know, the key is to keep pushing things along. I'm not here to say, gotcha, you missed the deadline, you're out, right? I don't really have any care in the world, right? I can compromise on some deadlines when absolutely necessary, right? And when everybody needs to laser cut all at once, I understand that. Maybe where I need to compromise. I don't compromise on understanding excellent A work, above average B work, average C work, right? I know what that looks like. That's where I don't compromise. So keep that in mind, right? Communicate, ask for help, and think a few steps ahead, help me help you, but sign up for that laser cutting time, that gives you a set deadline, and then when somebody says, well, I need your help, I go, well, I'm around, you know, I'm around Thursday, and Friday. You go, my laser cutting time's on Thursday. Okay. Let's set up some time on Thursday morning or Wednesday evening over Zoom. And we'll figure this out. Something like that. I case by case basis. That said, I don't often answer my emails without my computer. I'm just too old to crap to stay at home. I'm just too old to pull over. I've done it for so many years. It's just, I just don't, I have to be up at 5 a.m. on the road by 6. My schedule's down to the minute with my calendar. So just keep that in mind, right? If you ask for all those days, then it might be really early the next day before I see it. So if I win, for those who brought their prototypes, go ahead and bring those up carefully, make sure nobody bumps into you on the way up. Let's take a quick look at those. And see how it turned out. But I'm seeing some, at least from back here, they look pretty good. How did it turn out? I have an idea here. 2 layers. 2 layers. So if you want them to actually bend like that, think in terms of really thin paper. You can make something like this shit. Cardstock, paper. It's just a function of power and speed. Yeah, if it's too wobbly, too floppy, you might need to take down the edges to screw up the tape. Keep it from blowing around. But and you can put each piece in big little bits where it's a little gap like this and that, and they don't sort of keep it evaporate and they masking tape over it. Yeah, let's take a look. See. Hey, this is pretty good. This is your first idea. Well done. So for the next iteration, this is this. But now you're in your something each one. It's shipboard to yeah. So what I would say is you can move these together. They're going to become more rigid as you actually use it. I would say so you're going to use this. Now it's about popping it up. This almost there. Oh, it's these edges that really screw up. This one, that longer.
Yeah, this one, I don't know, I think I was pulling it away from the object and it's separating them, I think, a little bit.
Yeah.
But I think, like this.
Yeah, but what you can do is you just pull this one off. Be searching.
I think I might redo the whole thing.
Okay, well, you can do that. But what you can do, I would say is, and then here's what I would say. Try laser cutting components and try fitting them in here before you move them onto your second version. Make sure they fit. Otherwise, you're going to miss the first draft of machine components. Then you have the second one that's better. And then you can just basically rework the machine. Does that make sense?
Yeah.
So just think it through and say, this is going to be my first yeah, always needs to usually has the most pristine stuff to it, but without something like the notches or the right? So I mean, they just sort of like good job. Yep, another good one. Yeah, you zap it together. Alright, it's all about the shape. You got
I have one. And when I would come in the morning, he would open his eyes, Laura. They were learning our names. They learned your name and then talk to them. Learn. So that was his thing. He was using my name for other things to learn how to use our words. I mean, that was my idea. They were like prototypes of yours and then you could maybe I got it. But I mean, I came into the world and it was just like when I walked in, my robot was
There, and has machine vision.
she would look
Very
at me,
cool.
he